we're going to talk about the area of a triangle, and I know you already know the area of a triangle. Area triangle, or the area formula is 1/2 times base times height. But what happens in a case like this where you don't have a height, but I have an angle measure here, and I know two sides. Now I could draw a height. I could certainly drop a height, and then use right triangle trig to figure out the height, blah, blah, blah. I'm not going to do that. I'm going to actually show you a manipulation of this to find a formula so that when I know two sides and the included angle, like this diagram, that it's just a simple formula to plug it into, and you'll be done. So here is a very general rendition of my triangle. That's not a right triangle, with the altitude drawn, or the height altitude drawn here as a right triangle. And so what I could tell you is that the area of this triangle would be 1/2 times the base times the height, where this is the base and this is the height. And that's beautiful. But what if I don't know the height? What I want is a second relationship here, and that would be through the sine rule. And what I can tell you is that from this angle, the sine of C is equal to the height opposite over its hypotenuse, which in this case will be A. And solving for H, I will get multiply by A, gone, and H will be equal to A times the sine of C. Substituting in this piece for H up into here, I will get 1/2. Well, it would be BA sine C, so I'm going to rewrite it AB sine C. Now, as soon as I make that trig substitution, I don't call this the area anymore. Well, I do, but I don't represent it with capital A, because we don't want to get confused with the traditional area formula for a triangle of 1/2 base times height. So with the trig manipulation, I now call this area K. That's it. Simple as that. Now, if you forget, well, first off, you don't have to forget the formula. The formula is on the reference sheet. Yay. But if you forget it's there, you are welcome to, at any given time, going back to this problem, drop an altitude, find the height by taking the sine of 45. Sine of 45 is x over 8. You can actually find x and then plug it into this formula with a 1/2 times the 13 times whatever it is you found for the height, and you'll get your area. But it's so much easier with this, because here I have 1/2. Now, if this is angle C, then the two legs are my A and my B. And so it would be 8 times 13 times the sine of 45. And that's it. And then it's a calculator episode. And when I punch that in my calculator, I get approximately 36.7 to the nearest tenth. Nope, it's not. It's 36.8. Sorry. Because I have to round. 36.76955 is 36.8. Okay. So now we're going to talk about another piece, ambiguous case. Whoops, I didn't mean to do that. The ambiguous case. And so continue looking at this. And this will wrap up our concepts for applications. Okay, taking you back to geometry again. Triangle congruencies. If you are trying to prove two triangles are congruent, there were 4 triangle congruencies for general cases. Side, side, side. 3 sides of one triangle, 3 sides of another. Side, angle, side. 2 sides in the included angle. Angle, side, angle. 2 angles in the included side. Or angle, angle, side. 2 angles in a non-included side. Those are the only 4 triangle congruencies, other than hypotenuse leg, which is a special case for a right triangle. That is it. Now, the 2 that are missing, angle, angle, angle. Angle, angle, angle only proves similarity, because there needs to be an actual side 1-to-1 side ratio proven And so if you only have three angles, you know that they're similar, but not necessarily congruent. The other one is two sides and a non-included angle. And back in geometry, we probably wrote it like this, only because we didn't want to put a bad word in your notes. Okay, but let me tell you that angle, side, side, or side, side angle is not a triangle congruency, and it's not because we don't want to write a bad word on your notes. It's because if I give you two sides and a non-included angle, which means the angle that's not between the two sides, I cannot guarantee you triangle congruencies. Let me give you an example. Okay, so if I ask two people in the class to draw a triangle with these specifications, side A has to be 5, side B has to be 8, and angle A has to be 30 degrees. It is very possible for two completely different triangles to be drawn. So the first person might draw it like this, whereas this is A, and this is little side A, and this is little side B. The second person might draw it like this. Oh, very different kind of triangle. So in one case, this angle here is going to be acute. In this case, this angle here is going to be obtuse. And so you say to yourself, well, why is it? How can that happen? And why doesn't it happen all the time? Well, I'll tell you why it doesn't happen all the time. And what I'm going to do is I'm going to prove this to you through law of sines first. Okay. So let's go back to the original specifications. This is what's given. And so if I just draw myself a random triangle, I will put angle A in here at 30. Side A is the opposite side, that's 5. I'll put angle B here, and side B is 8. And what I'm looking to see is, does angle B even exist? Is there a measure for angle B at all? And if so, is there one or is there two? That's really what I'm looking for. Through law of sines, which says the sine of A over A equals the sine of B over B, I can throw in my numbers. And once I do that, because the 30 and the 5 are opposite and the 8 and the x are opposite, I'm going to cross multiply, and I'll get a ratio for the sine of B equals, well, 5 times the sine of B is 8 times the sine of 30. Now we all know that the sine of 30 is 1/2, so that actually is going to only be 4, but that's okay. So that means that the sine of B then will have a ratio, if you plug that into your calculator, of 0.8. 000, yes, but whatever. So when you inverse sine that ratio, you get angle B to the nearest degree of 53 degrees. Here's the thing. Now that we have learned about the unit circle, we know that this happens twice. This happens in quadrant 1, and it happens in quadrant 2. And in quadrant 1, my angle will be 53 degrees. But then I need to take this reference angle of 53 degrees into quadrant 2, and when I subtract it from 180, I will get an angle of 127 degrees. So there's actually two answers here. The first triangle will have angles of 30, 53, which adds up to 83, and then the third angle at C, if you will, I'll put a little C up here, will be at 7. So there's one triangle. The other triangle will have the given 30, but it'll have a second angle at 127. What you need to ask yourself then is there enough left for a third angle at C? And because 127 and 30 add up to 157, I can say, yep, 157, I'm left with another 23. Both of these meet the criteria for a triangle. So in this case, there are two triangles that are able to be formed. Here's a second example, and if I plop it into a triangle, I'm going to put my angle A here, and that's 70, and so the side opposite's 10, and then I'll put angle B here, and that's 7, and that's what I'm looking for. Does angle B even exist, and if so, is there one or two possible values? Those are the questions you have to ask yourself. So through law of sines, I did this quickly. Sine of 70 over 10 equals sine of B over 7. Again, keep in mind with law of sines, we're matching up the opposites here and here. So it's the sine of B over 7, sine of 70 over 10. When I do an inverse trig ratio, inverse sine ratio on this product here, so my ratio was 0.65778, etc. When I inverse sine that, that's sine to the negative 1 on your calculator, remember, the angle B turns out to be 41 degrees, which means, yes, angle B exists, 41 degrees. And my first triangle would be 70 degrees, 41 degrees. That together makes 111, which means the missing piece is 69 degrees. Those together add up to 180. Perfect. Triangle number 1. Triangle number 2 would say, yeah, but what if this is obtuse? What if this is in quadrant 2? Because remember, in quadrant 2, the sine ratio is positive. So if I take 41 degrees into quadrant 2, that means that my angle of rotation is going to be 139 degrees. So angle B could also be 139 degrees. Sine of 139 is going to be the same ratio. However, the given angle was 70. And with an angle of 139, there is no angle, unless it's negative, that's going to give you 180, which means the second angle does not exist. The obtuse angle does not exist. And this says there is only one triangle that's possible. Another example for our notes, we've got AB and angle A given again. So again, I just draw myself a quick reference. This will be my 74. Side opposite is 8. The adjacent side is going to be 11, because this will be angle B. That's what I'm looking for. So through law of sines, it'll be, again, these two go together. So it'll be the sine of 74 over 8. Oops, that's a 4. Is going to be equal to the sine of B over 11. Cross multiply, and the sine of B is going to be equal to 11 times the sine of 74 divided by 8. So basically what you do is you multiply these two and divide by the odd man out. Okay, so when you multiply, you get 1.3217. So that means that the sine of B is equal to that 1.3217. It is more decimal, but I rounded it to 4. When I do an inverse sine on this, if you haven't already noticed, when I do an inverse sine on this, my calculator gives me an error. More importantly, it gives me a domain error. That is because sine is never 1.3217. Remember, the sine ratio oscillates between -1 and +1. And when you look at the inverse sine function, remember that that inverse sine function, the domain is from -1 to +1. If I can refresh your memory what that looks like over here. So it's going to be, kind of like that, except this goes from -1 to +1. And of course, that's your pi over 2 and your negative pi over 2. You can't go to 1.32. 1.32 is outside the domain of this function, the inverse trig function. So this is an error. What that means is that angle B does not exist. It's impossible to build this triangle. And so therefore there's 0 triangles. If I look at it more logically here, let's say I give you a triangle with angle B or angle A at 74 degrees. And then I tell you I'm running up this way here at 74 degrees, 11 units. And then I only have 8 to get back. Hopefully your reasoning skills tell you that if you run up to here by 11, you need at least the altitude length here, whatever that is, that's the minimum amount that you would need to get back to actually form this triangle. I don't know what the height is. I could find the height. The height of this triangle would be equal to the sine of 74 would be the height over 11. So the height would be 11 times the sine of 74. And if I work that out, I get 10.6. So if I run up this way by 11 units, I need a minimum of 10.6 units to get back, and I only have 8. So this thing is going to fall short in here, and it's just going to dangle. And that is why I have no triangles. Okay, so now that I've given you 3 different examples, we're going to just practice these in class. And I'll show you a different method called the altitude method that some of you may pick up on and may prefer, but this law of sines will never fail you. As long as you remember that every time you get a trig ratio for sine, which is going to be positive, you need to check to see if there's possibly an obtuse angle also. So your answers are always going to be 0 triangles, 1 triangle, or 2 triangles. See you tomorrow.